Hello everyone. Thank you for deciding to watch this video. I am truly grateful for your attention and your curiosity regarding this material. And today we are going to expand a little bit on some of the concepts that we introduced in the first video. There are a lot of problems that can be solved in introductory physics by simply understanding certain symmetries in problems. And understanding vectors is the first primary step to understanding those symmetries. And understanding curvilinear coordinate systems is the second. Knowing this, the next natural step in our progression should be to discuss other curvilinear coordinate systems besides rectangular coordinates. Recall that our rectangular coordinate system is generated by using the field of the real numbers and projecting them into linear segments of ordered triples. Now when I say linear, I mean that each coordinate line, so to speak, is straight. There's no curvature to any of these lines. Its curvature is 0. Now, for most of introductory physics, that's a fairly useful approximation to the real world around us. Whenever, for instance, you have a block on a spring in Physics 1, it's very useful to think of it in terms of just one linear axis, x. Or if you're dealing with gravity and forces relating to that, it's very useful to think of a two-dimensional model of the problem using linear coordinate systems, where we would have, say, y-axis here and the x-axis here. However, the real world is almost always not so trivially simple. And in fact, it is only that simple when you have problems that exist locally on the Earth's surface, and only in very specific lab experiments where no sort of spinning or curving happens. Knowing this, we need to discuss how things curve in space, because obviously we live in a world where not everything moves straight. Sometimes we have things that spin, move along some sort of cylindrical symmetry, and so dealing with those requires us to change the way our coordinate system is set up so that it can easily adjust to those kinds of curved lines. Now, of course, we are all familiar with the traditional x and y coordinate system. You see this in basic algebra classes, you even see it in Calc 1, Calc 2, before you ever deal with 3 coordinates. Knowing this, we can ask, what is a two-dimensional translation for our 2D coordinate system into a rotation-based coordinate system, something that deals with rotations very easily? And so I'm not going to bother with a rough derivation, but I will simply tell you and ask you questions about what you think it should be. So I will start by simply drawing an axis, and it'll be a singular axis. And the special property of this axis is that its coordinates exist in such a way that they spin around some origin, O. Now that origin is the center of our coordinate system, which I uniquely choose to be wherever I see fit. And for this particular rotational coordinate, I will call it theta. Theta is a Greek letter. The fact that I call it theta does not have any particular significance. It is simply a variable I've chosen to express the rotation of this particular coordinate system. Now, I have one coordinate here, theta, but I have two coordinates here, x and y, and so in order for my dimensions to remain consistent among this transformation between coordinate systems, I need a second coordinate. So I want you to take a moment and think to yourself, if you haven't seen this before, what do you think that coordinate should be? If I've described a rotation about this axis, what is the second coordinate I would need to describe all of space around this kind of a coordinate system? Assuming you've taken a moment to think about it. The answer is, if I have every angle theta described in this coordinate system, then in order to describe all of space, the easiest way to do it would be to describe the distance from the origin, which we'll call r. Now, do not confuse r with simply the radius of a circle or the radius of some other object. R can change with respect to theta, meaning as theta changes, r can change as well, and vice versa. When thinking about this kind of new coordinate system, it's almost best to see a visual representation of what the paths can take. In Calc 2, you will see this. You will see that r and theta can change in very beautiful and creative ways. You can say, do something like this, and then continue around as theta continues spinning in its infinite circle. You can also take a form of hearts, and truly most interesting in my opinion, spirals. There are lots of different computations you can do to translate from our two-dimensional rectangular system to polar coordinates, but I will not bore you with them because, as I'm sure many of you who already have experienced this kind of mathematics, I don't want to bore you with any of the ridiculous computations that you have likely already done dozens of times. And for those of you who have no intention of seeing the mathematics expressed in any way other than what I do here, I don't believe it would be of much use to you, and I don't believe you'd find it very enlightening. So I will simply leave this as it is, and instead I will now ask an obvious question that has come into maybe a few of your minds. How do I translate this two-dimensional coordinate system into 3 dimensions? If I create circles or paths that resemble circles here, what do you think the natural extension to 3 dimensions would be for, say, a circle? If you can think of it, I applaud you, and the answer should be readily apparent. It is a sphere. Bit of a crude sphere, but it'll do the job. So now how do we express our coordinate system for a sphere inside our 3-dimensional space? Well, we already have a way of expressing circles and curves in 2D space, so I believe it makes sense for us to stick with those and try to figure out a way to work with those in this space. So why don't I take a plane of the circle, and we'll establish this to be our radius, or r, and we'll take this angle to be theta, the angle with respect to the circle in this plane. And you can build them up and you can build them down. And that should be, in some of your minds, exactly where our third coordinate is going to be, because we need 3 coordinates to translate to 3 coordinates. We can't change dimensions, that's not allowed. So if I'm going to be building circles or curves vertically, I believe it makes sense to do just as a globe would do and have both an angle with respect to the horizontal and an angle with respect to the vertical. So if we do that with respect to the z-axis, we can call that phi. Phi, again, is just another variable. It can be interchanged with theta regularly. And in fact, in most physics books, theta is actually up here and phi is down here. And I may make that switch later, if I so choose. If you're in a technical field like GIS, I believe one of them is lambda and one of them is theta, if I'm not mistaken. Now, we have our 3 coordinates here, r, theta, and phi, as opposed to x, y, and z. And there are means by which we can translate our coordinate in xyz to a coordinate in r, theta, and phi. I won't bore you with the details of the computations. Like I said, you can find many of them in the backs of textbooks like Griffith's E&M, which I have right here. We have several of the transformations between coordinate systems here, both for spherical and cylindrical. Cylindrical, you'll notice, is a bit similar to spherical in that we have some angle phi, this would be our theta in that term, s, which is the equivalent of r, and the z-axis is maintained. It is a very similar process to explain cylindrical as it was spherical. And if you're ever curious about doing the math, this is a good place to start. And in fact, this is the fundamental basis for most of the work you will need to understand before you can do any intermediate work in physics. So, highly recommend Griffith's Chapter 1. It is a significant boost in any knowledge you may have had before from either Calculus 3 or Calculus 2. Very, very well written as well. And so with our different coordinate systems, we can discuss a bit of the symmetries as to why we would want to use spherical coordinates, or perhaps even the cylindrical coordinates, which we saw before. Cylindrical coordinates are typically useful when you have any sort of linear property that you're trying to establish and you want to know something relative to the distance away from that line. In other words, it's like I'm wrapping a cylinder around that linear object, which we can assume to be a perfectly thin line in some cases, where the approximations are appropriate with our experiment. So cylindrical coordinates would be incredibly useful here. And spherical coordinates, as you will likely have guessed, are incredibly useful for anything regarding the surface of a sphere, which, as I'm sure a lot of you have noticed, occurs very much in nature. So our spherical symmetries can be made great use in, or rather, spherical coordinates can be made of great use in anything involving spherical symmetry. So the ways in which we would perhaps like to use spherical coordinates would be with a spherical shell, where perhaps something is moving along the spherical shell along some path, or even just a singular point. Say a point charge or a point mass. If you're dealing with a singular point that is producing some sort of field, vector field, no, not a coordinate field, not a field that we discussed in the last video, but a vector field, I can use spherical coordinates to get perfect symmetry around that point. And in fact, almost all of the fundamental laws of electricity and magnetism that you learn results from taking a point example of something or a line example of something and extrapolating it to all different types of other objects through something called the principle of linear superposition. The principle of linear superposition is by far the most important idea in introductory physics for you to learn, because it is through this idea that you can break down, I'd say, a good 50% of the problems in your intermediate classes down into something a bit more manageable. And what the principle of linear superposition says is basically this. Whenever you have some sort of either conservative vector field or you have some sort of change in energy that allows you to move things or adjust things in nature, I can deal with any sort of multitude of those forces or vector fields in such a way that I can add each of the individual contributions together. So if I have 3-point charges, and I have another point charge here, and let's say they each have some charge Q, and this one is minus Q. If I want to know the net force on this charge, all I need do is calculate the forces due to each of these 3 charges separately and add them together. That is the most basic idea behind the principle of linear superposition. And so, with that, I believe we can finally begin talking about physics. And I'm going to start with the next video with something that I'm sure all of you will find quite interesting, which is the idea of energy. And I hope to see you there. Once again, thank you so much for watching. I hope you enjoyed this video. I hope you enjoyed learning a thing or two if you haven't seen this before, and I hope you've enjoyed revisiting it if you have learned it before. Have a wonderful, wonderful day, everyone.